Hey everyone, welcome back to your math class and to lesson 22. Today we're going to be exploring angles. Again, this isn't going to be a super difficult lesson, but I just want to make sure that everybody has a solid foundation in these topics before we dive into the rest of the unit. So the plan for today's lesson is we're going to explore different types of angles, and that's going to take a few minutes. We're going to go over the different ways that we classify angles and how we measure them. Then we're going to talk about how we name angles. So not how we describe them in words, but how we name them, like when we're drawing diagrams and we want to talk about this angle instead of that angle, how we're going to name them. We'll talk about that. And then we'll talk about an interesting relationship between angles and polygons. We studied polygons a little bit last lesson. And then in our next class, we're going to start taking a look at triangles, which is going to build off some of the ideas that we learned here today. So angles are a measurement of the space between two lines or two line segments that cross each other, or the fancy word for that is intersect. So if you have one line like this and another line like that, then what you've got is here you've actually got four different angles. You've got an angle here, you've got an angle here, you've got an angle here, and you've got an angle here. So anytime that two lines cross or the two lines meet up at a point, remember from the fancy terminology last time that these would not be lines if they stop anywhere. Lines don't have endpoints, so this would be two line segments. But at any rate, we would typically be focusing on the angle here, although technically there's also this big angle way out here. So anytime that you have two lines that cross each other or meet up at a point or anything like that, you've got angles to start thinking about. And angles are measured in degrees. So just the same way that you would measure a length using meters or centimeters and time using hours, minutes, seconds, you measure angles, you measure the space between two lines or two line segments using degrees. And so basically degrees and this kind of measurement allows you to describe the difference between this angle and this angle. So this little guy, this little small angle in here, and this significantly larger angle out here. Degrees are what we use to quantify that, to put a number to it. And so we're going to look a little bit more closely at that today. Now, degrees can be subdivided. We're not going to worry about that in this class, but degrees are a little bit weird because when you subdivide them, you can do it with decimals, like you can have like 9.5 degrees, but there's also a stranger, more different system that's also used to subdivide degrees. So we're not going to worry about that in today's class. If we have some extra time at the end of a particular lesson or something, then we'll talk about it then, if there's one lesson that ends up being really short for some reason. Yeah, other than that, it's not really anything you need to know. Just if you ever see weird words and weird measurement systems come up when you're talking about angles, just be aware that that's a thing, but we're only going to worry about degrees in this class for the time being. So on the next slide, it's just going to be that diagram that you see at the bottom of the screen. It's just going to be a little bit bigger, and we're going to talk about it over there. So here are the different types of angles. So the ones that we're going to see the most often are the top three. So we're going to see this one, and this one quite a lot. So the first one over here in the top left, that is an acute angle. So that's less than 90 degrees. So this actually doesn't give a lot of context unless we first understand this guy in the bottom right, saying that a full rotation has 360 degrees in it. So that angle, if you've got like one, let me see if I can draw this out. So it's hard to sort of picture the rotation. So what I'm going to do is I'm going to draw out a few angles. I'm going to say, suppose you have an angle like this, right? And then what I say is, so you measure this angle, whatever, and then I'm going to say take this line that you used to build your angle, and I want you to twist it. I want you to turn it. So keep the bottom one flat, but then twist this one, and you see that this angle starts to get bigger, and that's because we've rotated the second one. So if you've got your angle kind of like this, I'm saying take one of your two sides that's making up the angle and twist it that way, and then keep twisting it. And if you twist it all the way around, so if I just draw out a couple more stages of that process, you have an angle like this where you've twisted it further that way. So the angle keeps getting bigger as you move one of the arms of the angle around. And then, if you keep doing that all the way until it overlaps the first one, you've done a full rotation, and that full rotation, that angle has a measurement of 360 degrees. So that's what we mean when we say that there's 360 degrees in a full rotation. So you can think of it like the minute hand on a clock over the course of an hour does a full rotation. It goes from up here, goes all the way around, and comes back to where it started. It's done a 360 degree rotation. So if you've ever done a 360, that's what that is, that you've done a complete rotation. You were facing one way, you turned around, and you kept turning until you were facing the same way that you started in. That's a 360 degree rotation. So now, if you take that 360 degrees, you can actually divide that very neatly. If you divide it by 4, 360 divided by 4 is 90. So that's this angle right here. A right angle is exactly 90 degrees, and you'll see that that's a quarter of the way around a full rotation, which makes sense because we've divided it by 4. So your full rotation, tracing out a full circle, the hour or the minute hand on a clock in an hour does a full 360 degree rotation. In 15 minutes, it does a 90 degree rotation. So it only turns a quarter of the way around the full circle. So that's a right angle. An acute angle is anything that's smaller than that. So again, if we go back to thinking about it like a clock face, so if you've got a clock, then your minute hand, actually I'll just draw some numbers on and then I'll use my laser pointer to sort of indicate what's going on here. So here's our clock, 12, 3, 6, and 9, and I'm not going to put in the rest of the numbers. And then we have our minute hand start here and go up towards the 12. So over the course of an hour, your minute hand will go all the way around once. That's a 360 degree rotation. In 15 minutes, it'll only go from here to here. That's a 90 degree rotation. So when it goes from here just to here, that's a 90 degree rotation. That's the angle covered by the minute hand on a clock in 15 minutes. Anything smaller than that, any angle that's smaller than 90 degrees, so smaller than a quarter turn, is called an acute angle. So anything that's smaller than the two arms of your angle making a nice corner, anything smaller than that is going to be an acute angle. So right angles end up being super important. For those of you that have seen geometry before, you already know that. For those of you that haven't, now you know that right angles are super, super important. So I'm going to get rid of that circle in the middle there. But yeah, so right angle is a quarter turn. So if I was facing this way, facing the camera, and then I turn until I'm facing directly to my left instead of straight in front, that's a 90 degree turn. That's a right angle. That's a 90 degree angle between where I started and where I ended up facing. You can't see where my arm is going, but you understand the point. So yeah, anything smaller than a right angle is going to be an acute angle. Now, something that's bigger than a right angle is going to be an obtuse angle. But you'll see here, so a right angle is exactly 90 degrees. An obtuse angle is greater than 90 degrees, but less than 180 degrees. Now, 180 degrees on our clock looks like this, going from the 12 on top to the 6 at the bottom. That's so completely turning around and facing the other direction. That right there is a 180 degree rotation. So anything that's bigger than 90 degrees but smaller than 180 degrees is what we call an obtuse angle. And then when you've got exactly 180 degrees, you've got a straight angle. So we're not going to deal with straight angles very much because it's not often that you have an angle that's just the two line segments are just pointing in opposite directions, because then it just looks like one big line segment. So we're not going to have to worry about straight angles very much. We're not going to have to worry about reflex angles very much, and we're not going to have to worry about full angles very much. So it's just these three at the top that we really need to understand well. So once again, if you've got an angle that, so for instance, if I draw an angle like this angle in here is less than your quarter turn from your, if you think, it's really helpful to think of it like the minute hand on a clock, which starts at the 12 and then it goes all the way around. I think the visuals might be sort of mirrored in what you're seeing in the video, but your minute hand starts at the 12, goes all the way around and comes back to the 12 over the course of an hour. That's a 360 degree turn. Just that first quarter from here to here that's a right angle. And so anything smaller than that is going to be an acute angle. And anything bigger than that is going to be an obtuse angle. And then, like I said, we're not going to really worry about these bottom three. So make sure you know what those top three are and sort of what the difference is between them, because that's going to come in handy in future classes. Now, for the most part, like up until it comes to the point where you might actually have to measure angles, most of the time you can just look at them and you can tell. If you just know what a right angle looks like, it looks like any of the corners in a square, right? So that's the easiest way to think about it, is a right angle is what all of the corners on the inside of a square look like, a square or a rectangle. They all have 90 degree angles that look like this. Acute angles are smaller than that, so the space between the two sides is smaller, and obtuse angles are bigger than that, so the space between the two arms here is bigger. So that's all you really need to know about angles, but I just want to make sure that we're clear on that. So if there's any questions, if there's any concerns, just let me know in the comments and we can talk about that more fully later on. Now, naming angles is something that ends up being important whenever we need to draw out our angles to solve a problem or whatever. Mathematicians love to put names on things. We saw this in our previous unit when we were talking about algebra, and we were saying, oh, let M represent the whatever number of pairs of mittens or whatever, right? So it's just to give names, usually just a letter or two. Mathematicians love giving names to, variables and line segments and vertices and whatever. Vertices might be a new word, but yeah, so we're just going to look at how we name angles as well. So just reading off the slide here, it's useful for us to name the endpoints of the two line segments that make up the angle that we're exploring, as well as the point where they meet. So if I draw out an angle, right, we've got an endpoint here, we got an endpoint here for the two separate line segments, and we got the point where they meet up. So we can give names to all three of those, and it can be whatever. It can be ABC, it can be ABO, like in the diagram down there. Typically, it'll be 3 letters in the alphabet where just sort of in sequence. So it'll be something like PQR or, WXY or whatever, right? So that's normally how it is. You could do whatever you want. You could, if your initials are like, I don't know, MRJ, then great, go with MRJ. Like, it doesn't matter, right? But so we give the endpoints of the two line segments a name. So just usually a letter, A, B, C, something like that. And we give the vertex. So that's the point where the two angles, or where the two arms of the angle meet. That's called the vertex. we give that a name as well. And the word I said a couple of minutes ago, vertices, that's just the plural of vertex. So if you're talking about two angles and one's got a vertex here, one's got a vertex there, the two vertexes, the actual plural is vertices. Yeah, so in this example, the way we would name the lines is, or really the line segments, let's just ignore the arrows on the end there. If we just treat the angle as A, O, and B, the three orange dots there, then we've got one line segment up here, which has the endpoints A and O, right? And we've got this other line segment down here that's got the endpoints B and O. So we could call this line segment BO or OB. That's just the name of the line segment. And then this one up here is either named AO or OA. So that's how we name the line segments. And then the way that we name the angle in between is we start with one of the line segments at the endpoint that's away from the angle. So for instance, this A, then we name the vertex, then we name the other endpoint of the other line segment. So if we're talking about this angle in here, this would be angle AOB or angle BOA. So it doesn't really matter because it's going to look the same either way, but that's how we name our angles. So you give names, you give one letter names to the endpoints of your two arms. That's what we call the line segments that meet up to make the angle. We give a name to the point where they meet up, and then the name of the angle is one of the endpoints, the point where they meet up, and then the other endpoint for the line segment. And that's how we name our angles. So some key takeaways from what we've just looked at over the last couple of slides. First things first, they're 360 degrees in a full rotation. So if you've ever seen anybody on like a skateboard or a snowboard or a Formula One car and they do a 360, that means that they've turned all the way around and they're facing the same way as they did at the start. Similarly, if you've ever heard the expression to do a 180, like to change your mind on something and go from, completely loving something to hating something, or wanting to do something to not wanting to do something. To do a 180, that's going from I was going in this direction, now I'm going in that direction. I've completely flipped myself around, I've completely changed my mind, or I'm completely different, completely the opposite of what I used to be, whatever. That's where this comes from as well. This comes from geometry, that because if you've got one of your arms of your angle pointing that way and the other one pointing that way, they're pointing in opposite directions, and the angle between them is 180 degrees. So that's where that comes from. A very important thing that we need to know is that right angles are drawn using a little square instead of an arc. So what does that mean? That means that if this is a 90-degree angle up here, we'll mark that in by drawing a little, like making a little square in the corner, instead of drawing an arc. If you draw a little arc, like a little part of a circle, then that means that it's not 90 degrees. It's either bigger or smaller, but it's not 90 degrees. So what you'll see is that if I wanted to communicate to you guys that this thing that I've drawn is a square, let's say, very badly drawn square, right? But if I give this to you on a test and for some reason I've put a hand-drawn square on there, right now, it doesn't look like they've got straight lines. Maybe I write in the text, assume, pretend everything is a straight line because we're working with polygons. But then I want to communicate that this is a square. So first things first, I'm going to show that all the sides are supposed to be the same length by putting those little tick marks that we talked about before. So there we've got the tick marks. So that says that all four sides are the same length as each other, even if on the paper they're not actually. This is me telling you that they're supposed to be the same length, and I'm just bad at drawing them. But then if I want to tell you that all the angles are 90 degrees, even if they're not actually 90 degrees on the page, but I meant for them to be 90 degrees, then I'll draw in these little squares to show that they're supposed to be 90-degree angles. If they're not, if it's a different shape, if it's something like this, something like that, you could still have that all four sides are the same length, right? I could still put tick marks here, 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 and here. But now the four angles aren't right angles, so I can't draw in the little squares. I have to draw in the little arcs instead. So something like that and something like that, right? And actually I could have colored two of the angles differently or whatever. But so this would be a difference between showing that the angles are supposed to be right angles versus the angles are just whatever. They're not right angles. They might be smaller, so they might be acute angles. They might be larger, so they might be obtuse angles, but they're not exactly 90 degrees. So that's an important thing to note as well. And then, of course, how to name angles. Again, I'm not too worried about like the proper way to name angles and stuff. I'd rather you guys understand the concept so that you can use them later on than to get bogged down in like, oh, I have to figure out how to name things properly. Because I've done work with angles like sort of out in the real world, done more work with angles that use some of the ideas that I've learned in geometry class, but I'm not sitting there naming my sides and my angles and all of that stuff. So I'd rather you guys know sort of the concept rather than get bogged down in all like the terminology and stuff. So I hope that makes sense. Now, a little sort of add-on is if you're feeling fancy, there's a special way that mathematicians like to write the names of line segments and angles, just because a lot of times with a lot of problems, you're dealing with a whole lot of different line segments and angles and shapes and this and that, and there's a lot going on. So one way that you can talk about your line segments is this is the same diagram we were looking at before, right? A, O, and B, those orange dots. But now instead of writing just OB or BO to talk about this guy down here, you can write OB and then put a little line over top of it. That's to tell you I'm talking about a line or a line segment right now. And then same thing for OA or AO. You write down OA, AO, whichever one you prefer, and then you can put a little line over top of it to say I'm talking about a line. And this is really helpful because if you're talking about, here you're talking about a line, here you're talking about an angle, here you're talking about a triangle, here you're talking about something else. You've got all these things that just have these names like PQR, STU, like not meaningful names, right? You've just got, oh, this is angle JKL, but it looks really similar to triangle JKL. Like, it's just, there's a lot of letters going on that don't mean anything. So when you're talking about line segments, it'll be two letters with a line over top. And when you're talking about an angle, you can draw in this little mini acute angle here and then name your angle the way we did before. So AOB or BOA, and you can draw in the little angle before it. And then similarly with what I was just saying about triangles, you'll see I've written on the screen that when we start working with triangles, we'll see something similar there, is that you might have a triangle and then you name your triangle something like, I'm going to call this point J, this point K, and this point L. So if I want to talk about this angle right in here, well then I have to talk about point J, point K, and point L, right? That's one of the endpoints of the line that's making up this side of the angle, then the vertex, K, and then a point on the other side that's making up the angle. So this would be angle J, K, L, the angle in black there. But if I wanted to talk about this whole triangle and talk, maybe there's a second triangle in the question and that's called triangle ABC, then this whole triangle would be called triangle JKL because those are the names of the 3 points. So you can see how sometimes this little triangle and this little angle here make all the difference in being able to tell apart. Am I talking about an angle here? Am I talking about a triangle? What's going on? So that's just a little fancy thing. You don't need to know that, but it might be helpful to you going forward as we explore more complicated geometry. Last important thing I want to talk about in this lesson is a very useful property that polygons have. So now we're connecting angles back to polygons from last lesson. So I'm going to read it out and then we're going to unpack it a little bit. So the sum of all the interior angles of a polygon with n sides is n minus 2 times 180 degrees. What is that? Okay, so first things first, easiest part, the sum. That means an addition problem. So addition problem of what? The interior angles. So that means that you have some polygon, right, which is a closed shape. So something like just some weird shape, right? So there's our polygon. Our interior angles are all the angles on the inside of that shape. So this is an interior angle, 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 and this is an interior angle. Those are all our interior angles. So the sum of all of those, so whatever each of those angles measurements are, add them all together, and you'll always get the same number if the polygon has the same number of sides. So in this case, our polygon has 1, 2, 3, 5 sides, right? So we've got our 5-sided polygon. So it doesn't look like a typical pentagon, but it is a pentagon. It's just not a regular pentagon, but it's a 5-sided shape. So because it's a 5-sided shape, n is equal to 5 because it's a 5-sided shape. So that's what this is saying with n sides, right? That means from our algebra unit, that means you can sub in whatever number makes sense for what you're looking at. So without going through and actually adding all of these together, no matter what polygon or no matter what pentagon you have, what 5-sided shape you have, adding up all of these angles on the inside of the shape over here will always come out to exactly the same number. Now, what number is that? That's going to be this thing. So n minus 2, well, right now n is 5. So that's going to be 5 minus 2 in brackets times 180 degrees. Oh, that's a horrible 8. Sorry. Times 180 degrees. So 5 minus 2, that's 3. Times 180, so that's going to be 540 degrees. So every pentagon, no matter how you draw it, has 540 degrees as the sum of all the angles on the inside. And that's true of every single pentagon. Similarly, for a triangle, it's always 180 degrees because n for a triangle is 3. So it's a 3-sided shape. So n here, this is 3. So 3 minus 2 is 1 times 180 degrees is 180 degrees. So for a triangle, and you can explore this diagram more closely on your own, that a triangle, no matter what triangle you have, if you add up all the angles on the inside of the triangle, it'll always come out to exactly 180 degrees. If you do it for any 4-sided shape, so it could be a square, could be a rectangle, could be a kite, a trapezoid, a parallelogram, a rhombus, whatever, right? Any 4-sided shape, any quadrilateral, if you add up the 4 angles on the inside, you will always get 360 degrees. For a pentagon, like the one we just looked at, it'll always be 540 degrees. For a hexagon, a 6-sided shape, it'll always be 720, and so on. So you're not going to need it for most of these, but it'll be very useful when we're talking about triangles and squares, or just triangles and quadrilaterals, 4-sided shapes, because you don't have to measure every angle every single time. And so if you're ever doing like construction work, if you know 1 or 2 of the angles in your triangle, you can figure out the rest of the information that you need without measuring it. You can just do the math because you know this property about the sides in your polygon and what the sum of all the angles on the inside must be. So I know that's been a lot of information. Just one last quick note is that if you don't have a protractor, it might be useful to get one. I have not figured out what anything like a test or a quiz might look like for our geometry unit, but if you guys could all get protractors, or if you have protractors at the school or something, if somebody could let me know that that is something that's available to you, then it's something that we can talk about is how to go ahead and actually measure angles or draw our own angles using a protractor, which is this thing. So if any of you have a geometry set and you've got a ruler and then a whole bunch of other things that you've never used before, this is one of those other things that you've never used before, and it's super useful for drawing angles. So, like I said, that was a lot of stuff that we kind of went through in this last couple of lessons, and in the next lesson or two, we're going to start putting different pieces of information together. So we've talked a little bit about polygons, what they are, some names of different ones, and how we draw out, that two sides of a polygon are the same length, right? And we've talked a little bit about angles, so acute angles, right angles, obtuse angles, just, what the differences are, how we name angles, things like that. So right now it's just a lot of information. Next class onwards, we're going to start putting some of those pieces of information together, and we're going to start to learn some things about, in particular, triangles. And then as we go forward, we might explore some more complicated topics as well. But triangles are awesome, and honestly, we could spend our entire unit just talking about triangles, but that's where we will start in the next class. So, as always, if you have any questions about the unit, about the content so far, I know you guys are back like on your own kind of self-governing the math class now. So if you have any questions or concerns, please don't hesitate to reach out to me. I do have a bit of a hectic, kind of crazy week ahead over the next few days, so it might take me a little while to get back to you, but I am here, I am available. Let me know if you need anything at all, and I will be more than happy to help. But yeah, that's it for today. So if I don't hear from you between now and the next class, then I'll see you then. Have a good one.